Welcome to this video. In this video we're going to discuss the auditory system. Okay, so let me begin by giving you an outline of the topics that we're going to discuss in this video. So I'm going to start off by discussing what is sound, which is actually probably going to be the most complicated bit of the video, the most difficult to understand portion, because that's going to be a bit of physics. But it really is essential to understand what sound is before we can talk about the auditory system. Once we've talked about what sound is, we'll then begin with a lot of anatomy. Indeed, there's going to be a lot of anatomy in this discussion, because we're going to need to know the structures of these tiny little parts of the ear in order to understand how it's all going to work. So we will start off by looking at the structure of the external portion of the ear that you can see, the auricle, also called the pinna. We'll then talk about the temporal bone, which is where the other portions, the inner portions of the ear are going to be contained, and then we'll work our way along. We'll have a look at the labyrinth. We'll take a long time to discuss the structure of the labyrinth. And then what we'll do is we'll follow the entire pathway along of how auditory information is going to be transduced into electrical signals. After we've seen the transduction process, we'll then have a look at the central pathways where this information is going to go in the central nervous system, and we'll follow the sensory information up to the primary auditory cortex. We will not go beyond the primary auditory cortex, because at that point it becomes much less well understood and we enter the realm of psychology, and that's for a different video. So we will just follow the path of the auditory information up to the primary auditory cortex, and then we'll call it quits there. Finally, we'll end the video with a discussion of the different types of deafness. In particular, we'll discuss conductive deafness and sensorineural deafness, or if you prefer the more politically correct way of putting it, hearing loss rather than deafness. Okay, so let's begin then with what is sound. And as I say, this is going to be the most complicated portion of the entire video, so I'll just put a little title of sound here and then we'll discuss this. So, sound is not really a thing. Instead, it's a propagating disturbance in air molecules. It's a wave. It's like water waves. The water wave isn't really a thing in itself. Instead, it's a propagating disturbance of the water molecules. And sound is very similar to that, but in air instead of water. Okay, so let's just go over air. So I'll remind you that air is made up of loads of molecules, so a lot of nitrogen molecules and a lot of oxygen molecules. For our purposes, they're just air molecules, so we won't distinguish between the different types of air molecule. So the way I'm going to draw some air then is like so. These little dots will represent the air molecules, so there's going to be air molecules all over the place. So this is representing the air molecules of some air here. Okay, and before I just discuss what sound is, let me just remind you of the concept of pressure, because the concept of pressure is a nice way of communicating what sound is. We can draw a nice graph for what sound is if we understand the concept of pressure. So I just want to make sure that everyone understands the concept of pressure. So pressure is very much so related to concentration, but it's a slightly more complicated concept than concentration. Pressure has to do with, if you were to draw a little box around some air, so if I draw this here, so pressure is all to do with, if I was to draw a little box around some air molecules like so. There we go, and this will be a three-dimensional box. I'll try and draw it to make it look three-dimensional like so. So here is my little box, and it will have lots of air molecules in. So what's pressure to do with? Pressure is to do with how much force would there be on the walls of this box because of the air molecules inside it. Now you have to understand that these air molecules, they are not just stationary, they're moving around all the time, so they're flying all over the place. And how fast are they moving? Well, that has to do with what the temperature of the air is. The higher the temperature, the faster the air molecules will actually be moving, the more energy they will have. Indeed, that's what temperature really is. It's all about how much energy the molecules of that substance actually have. So the temperature of a substance has to do with how much the individual molecules of that substance are moving around. okay? And they will be bashing into the walls of my box here and exerting forces outwards. So on this wall I have a force going out like this, on this wall I have a force going out like this, on this wall I have a force going out like this. So there'll be a certain force outwards on the wall of my box, and that is what pressure is about. The pressure of air or of water or of something, okay, has to do with how much how much force you'd have exerted on the walls of a little box if you put the little box around a bit of that substance. Okay, so if we think about what is going to determine the pressure then, what is going to determine the pressure? How much force is going to be exerted on the walls of this box? Well, it's going to depend on the temperature, because the temperature determines how much energy each of the molecules has, and how much energy each of the molecules has will determine how much force, well, the speed that it's moving at, and therefore how much oomph it will bang into the wall with, and force is of course the concept of the oomph. Okay, so temperature will of course be involved here, but also concentration. If we have a huge concentration of molecules in there, then we'll be getting molecules hitting the walls more often and therefore more force. So in fact the formula for pressure is that it is nRT over V, and this of course, if you've ever studied thermodynamics, you'll recognise this. This is what's known as the perfect gas equation. Okay, so let me just tell you what the different symbols in this equation mean. So T is temperature, okay, and this will be in degrees Kelvin, so you won't do it in degrees Celsius, you'll do it in degrees Kelvin from absolute zero. So remember, the way of converting from degrees Celsius into degrees Kelvin is by adding 273 onto the number. Okay, remember, minus 273 degrees Celsius is 0 degrees Kelvin, absolute zero. Which is where the molecules would effectively have absolutely no energy. So it's a far more sensible temperature scale to use than degrees Celsius. Okay, so that's temperature there. Then what are the others here? Well, N here, this is the number of molecules in the box, okay, and it's the number in moles. So this is number of molecules, and we don't count them as in count every single molecule. Instead, what we do is we do it in moles, and remember, all moles is a conversion factor. So remember, 1 mole of molecules is the Avogadrian constant, so 6.022 times 10 to the power of 23 molecules. Okay, so this is what we call the Avogadrian constant, or N subscript A. So remember, it's just a convenient way of expressing the number of molecules that you have, because in reality, in any decent sized box, you're going to have a huge number of molecules. So instead of counting it in terms of the absolute number, we count it in terms of how many of Avogadrian constant number of molecules do we actually have, i.e. how many moles do we have. Okay, V is then the volume, and this will be in meters squared if we want our pressure to be in pascals. Of course, if you did this volume in a different unit, you'd end up with pressure in a different unit as well. So volume in meters, oh sorry, not meters squared, meters cubed. Area will be in meters squared, sorry. Volume is in meter cubed there, so meter by meter by meter. Okay, so we can see that if we take the number of molecules and divide it by the volume, effectively we've got the concentration of molecules there, and we're timesing it by the temperature, and then we're timesing it by this thing here, which is just the universal gas constant. So this is just a constant, a conversion factor to make the numbers all work out. So this is the universal gas constant, and this has a value which I believe is 8.31, although don't quote me on that, but the point is that it is just some constant, okay, just to make the equation work out. So if you take a little box like this, you plug in the number of molecules that you actually have in there in moles, you times it by this constant, the universal gas constant, you times it by the temperature, and then you divide it by the volume of the box in meters cubed, you will then get the pressure which will be in pascals. So pascals is the normal unit for pressure, well, one of the normal units for pressure, and pascals is newtons, which is the unit for force, per meter squared. And that makes complete sense because pressure is all about how much force we've got on the walls of our box, and this is giving us a density of the pressure effectively for a certain amount of area of the box. So this is saying for a certain amount of area, for a meter squared, how much force would you have on that surface of the box. Okay, right, so that's what pressure is all about. So I hope you can understand that it's very much so related to concentration. Indeed, it's just concentration times by some constant and then times by temperature. That's the important difference here. But it's very much so related to concentration. So as long as we're keeping the temperature constant, the only thing that can change the pressure is by changing the concentration of the air molecules, and that's going to be important for us to understand when we come to discuss sound, which we're going to come to now. Okay, so there's a reminder of what pressure is. Now let's discuss what sound actually is, and for this I'm going to recruit the example of a xylophone. So I'm just going to draw a little xylophone here, so we'll view the xylophone from above. So I'll just put a few little metal portions on. So here is one bar, here's a shorter bar, and here's a shorter bar still. So this is supposed to be a xylophone, and we're going to have a little beater which we can use to hit the bars of the xylophone. Okay, so let's start with this big bar here that I'm now colouring in green. So let's say that we hit this bar of the xylophone. What is going to happen? Well, we're going to get sound being generated, but how is it actually being generated? Well, let's think about what's going to happen to the bar. When we hit the bar, what's going to happen is it's going to oscillate upwards and downwards, upwards and downwards. So if I just draw the bar from the side here, what's going to be happening is initially when we hit it, it will be going downwards, but then it will be coming back upwards, it will go down, it will go back up, and it's oscillating upwards and downwards, upwards and downwards, upwards and downwards, and this is what creates sound, because what's actually going to happen when this bar of the xylophone oscillates up and down like that is it's going to be affecting the concentration of air molecules in its vicinity. So for instance, when this bar moves downwards, can you see that what's going to happen to the pressure of the air here? Well, the bar's moving downwards. That means these air molecules are going to become more spaced out because there's a new space opening up, if you like. So just to exaggerate this out, imagine that the bar has deformed downwards. In fact, I'll just draw this like so. So here's the bar deformed downwards, hugely exaggerated, but it gets the point across. You can now see that the bar has effectively pushed air molecules up here, and it's spaced air molecules out here. So if I draw some of these air molecules in, so let's draw some in here. So here they are originally nicely spaced out, and the same will be true below the bar here. Again, they'll be nicely spaced out. And now what's going to happen is above, they've got loads more space now, so they'll be much more spaced out here, and then below they'll now be much more compressed up. Okay, so the xylophone bar has spaced the air molecules out up here and compressed the air molecules below it together. And what's going to happen is this, excuse me, this change in the pressure, this will change the pressure after all, because we haven't changed the temperature, but we've altered the concentration, so the pressure has gone down here. What will happen is this will propagate forward, and the reason is that if we go up to here, this portion of air up here, the air molecules are still at the same concentration, they're still at the same pressure, but now down here the pressure is lower, and air molecules will tend to move from areas of higher pressure to areas of lower pressure. So what will now happen is molecules up here will move down to here, and that will make this area's pressure drop because molecules are leaving it, and this will continue on. So the air molecules up here, they will now be at a higher pressure than the air molecules at this position, and they'll move from here to here, and you'll gradually get this propagation of this area of lower pressure. So just drawing this on, well, how should I draw this on? So let's say, viewing this in a different plane now, let's say this area has got lower pressure, just like the area above the xylophone bar here. What's now going to happen is air molecules from the neighbouring area are going to move from their area to the area of lower pressure. And by the way, this area of lower pressure is known as an area of rarefaction. So rarefaction refers to an area of lower pressure. So air molecules are going to move to the area of rarefaction, and that will lead to this next area on from the area of rarefaction, now becoming an area of rarefaction itself. Okay? And now if we think about the area along from that, it will now have a higher pressure than this area, so air molecules will move from it to here, and it will become an area of rarefaction. Okay? And then the area on from that, it will now have a higher pressure than this area, so air molecules will move from it to there, and hopefully you can appreciate that what is happening is this rarefaction is propagating along. This is what I mean by saying that sound is a disturbance in the air molecules. It's a propagating disturbance in the air molecules. This area of rarefaction is propagating along through the air, and that's part of what sound is. But sound's more than that, because now, let's think about what the xylophone bar is going to do next. It's now going to bend back in the opposite direction, so it's going to now oscillate back up to look like this. Again, hugely exaggerated, but it gets the point across, and this is going to do the exact opposite thing now. The air molecules above the xylophone bar now are going to be hugely compressed up. Okay, so you're going to get an area of high pressure like we had below the xylophone previously. Okay, and an area of higher pressure is now called an area of compression. Okay, so the air molecules have been compressed together, and this area of compression is also going to propagate through the air. You see, because now the area of air, or the volume of air above this volume here, so here's the area of compression, or the volume of compression rather, and then above that we have a volume that has normal pressure, the normal pressure of the air. And now what's going to happen is air molecules from this area of compression are going to move from here to here. So I'll draw this on. So they're going to move from here to here, and of course that's going to raise the pressure here, so it's going to lead to compression here, and then that will propagate onto the bit above that, because this is now an area of compression, and above that you'll have a volume where the pressure is normal, so it'll just propagate along. So sound is actually these alternating propagations of rarefaction and compression, and they're produced by these oscillating objects. In this case, the xylophone bar is oscillating backwards and forwards, and it will be doing so at a certain rate, and that rate at which the xylophone bar is oscillating backwards and forwards will determine the rate at which you're getting rarefaction and compression propagating through the air. And that is what sound is. It's this propagating rarefaction and compression, propagating waves of rarefaction and compression. And this means that we can draw a very nice picture of this. So again, or rather a very nice graph of this, depending on your opinion of graphs. Okay, so let's say that we have a xylophone bar here. Okay, and I know I'm drawing it at an odd angle, but this is the nice way to show the picture. So let's say we have this xylophone bar here. So we're looking at the bit above the xylophone bar in an odd angle here. Okay, and the xylophone bar will be oscillating backwards and forwards. What we can now say is, let's plot a graph of what the pressure at a certain point will be doing. So I pick a certain point here, and I'm now going to plot a graph of the pressure of that point versus time. Okay, so here, this is the graphs that you often see people drawing of sound to represent sound. This is why we need to understand the concept of pressure in order to really understand the concept of sound. Okay, so I've picked a certain point, and now I'm going to plot the pressure at that point against time. Now let's say I have not struck the bar of the xylophone yet. So far the bar of the xylophone hasn't been struck, and therefore the pressure will just be at a constant level, which will be air pressure. So this is the normal air pressure here. Okay, so it's just stuck at a constant level at the moment. Okay, and now let's say I actually strike the xylophone bar and it starts oscillating backwards and forwards. When it oscillates upwards, that will cause a propagating region of compression, which will come to here. When it oscillates downwards, that will lead to a propagating region of rarefaction. So let's say I firstly strike it so that it goes downwards firstly, so I bring my beta here and I strike it downwards. Then what will happen is I'll get a propagating region of rarefaction. So what will happen is eventually here I'll get a region of rarefaction, so the pressure will go down, but then as it oscillates back towards this point, so it oscillates forwards, then I'll get a propagating compression coming forwards. So what will start to happen is, I hope you'll agree, I'll get something that looks like this. So as this continues to oscillate, the pressure at this point, and indeed at any of these points, I just chose this point at random, it wasn't a special point at all, you could have had whichever point you like, the pressure is going to oscillate in this sinusoidal way, like so. And these are the pictures that people often draw of sound. They draw it like this, and what they are showing is the pressure at a certain point. However, as hopefully you get from my description here, this isn't particularly helpful in understanding what is helpful, but it's not really the utter core of what sound is. It's this propagating compression and rarefaction that is propagating not just at a single point, because this is just plotting it for a single point, but it's all over the place. Okay, it's not just this point that will have this going on, it's all of these points. So understand this graph, but also understand truly what sound is. It's the air molecules are moving and that you're getting this alteration in air pressure all over the place that is propagating forwards. Another description, another key word that I feel that I cannot leave out is the description of sound as a longitudinal wave. Now all that means is that the oscillation that is occurring as part of the wave, so in any wave there's always some sort of oscillation. The oscillation that is occurring as part of the wave is in the direction that the wave is actually propagating. Now, when you look at this picture here, you would be tempted to say, oh, sound is a transverse wave, because look, this looks like the pictures that you generally draw of transverse waves, but this isn't truly what the sound wave actually is, and that's why you need to understand this part of the story, not just this graph here. You see, the oscillation that occurs in sound is the oscillation of the air molecules. They are moving in a certain direction. So for instance, in this picture here, let's do it. So when this propagates forward, or oscillates forward rather, when the bar oscillates forward, we get the air molecules compressed up, and then they're moving on to the portion of air, the portion of space in front of them, and then so on. It's propagating forward. So the air molecules are what are oscillating in sound, and they are moving in the same direction that overall the wave is propagating, which is why sound is described as a longitudinal wave. So hopefully you appreciate that the sound wave is going to move in this direction. Which direction are the air molecules actually moving? Which are the things that are actually oscillating in the sound wave? Well, they're also moving in this sort of direction here. That's why sound is described as a longitudinal wave. They are not moving in a direction perpendicular to the direction of the wave. That's how water waves would work. You presumably know that water waves, the direction that the water molecules are moving is perpendicular to the direction in which the wave is propagating there. So sound is described as a longitudinal wave. Okay, excellent. There are a few more concepts that I want to bring up with sound. The first thing that I want to point out, which I hope will help you understand this further, is that there is no sound in space. And the reason is, of course, that space is a vacuum. There are no air molecules. And without the air molecules, sound doesn't exist. Without a medium, it doesn't exist. It's not a thing in itself. It is an oscillation of the air molecules. And if you have no air, you can't have an oscillation of air molecules. So hopefully that will just nail this concept across, that if you were to shout in the middle of space, no one would hear you because there's nothing to propagate it through. Okay, right. The next two concepts that I want to come up with, or discuss rather, are the concept of the pitch of a sound and the concept of the amplitude of a sound, and this is why I've got these other bars of the xylophone here. So we'll start off with the concept of the pitch of a sound. So the pitch you can also call the frequency of a sound, and it has to do with how frequently you are going to oscillate between rarefaction and compression, rarefaction and compression. So what's the rate at which this wave is actually going to be occurring? And this is why I drew the xylophone as having these multiple different bars. You see, these different bars are going to give different pitch sounds, as you will know from being a child and playing with a xylophone. The larger bars, they give a more low pitch sound, and the little bars, they give a more high pitch sound. Okay, so why is that? What is the actual physics behind that? Well, the larger bars here, the lower pitch sounds, when you hit those with a beta here, they are going to oscillate backwards and forwards at a lower rate than these smaller bars. So when you hit a smaller bar, the rate at which this is going to be oscillating backwards and forwards is going to be much, much higher. And that means that the rate at which it is going to be generating rarefaction and compression is much, much faster. And that's the pitch of a sound, i.e. how quickly you are going between the rarefaction and compression, rarefaction and compression. It's actually best seen in terms of this graph here. You see, if I now made this bar of the xylophone smaller, so I turned it into one of these more high-pitched bars and hit it, the graph that I would now get would maybe look something like this instead. Okay? You can see that we're going between rarefaction and compression much more rapidly than previously. Okay, what's the reason for that? So I've now got this smaller bar. When I hit this smaller bar, it will be oscillating backwards and forwards more rapidly, and therefore it will be generating rarefaction and compression more rapidly, and therefore the pressure at a single point will be oscillating between being below the average air pressure and being above the average air pressure more rapidly. Okay, and that is what the pitch of a sound is all about. It's all about how many waves of rarefaction and compression you're actually getting in a certain time period. So you would measure this in hertz. So hertz means waves per second. So how many waves do you have per second? So what you do to actually measure this is, if you were a little man, let's say here's the little man, standing at a point, measuring the pressure, you would be counting how many of these complete waves do we have in a second. So this is a complete wave. You've got the rarefaction, then the compression, and then you're back to normal pressure for a moment. That's the end of a wave, and then you'd have another cycle of that, and you need to count how many of these do you have a second, and that would be the frequency. Okay, and that would determine how high-pitched the sound is. So high-pitched sounds, I'll try and do one. High-pitched sounds like that, they are sounds where you are getting this oscillation between rarefaction and compression occurring very rapidly, very high-frequency oscillations, whereas much lower sounds, they are much slower rate of alternating between rarefaction and compression, much lower frequency. Okay, so these graphs are a very nice, easy way to see what frequency actually means. That's where these graphs actually become useful. Okay, so that's what pitch means. The other concept that's really important is amplitude, more crudely known as loudness of a sound. What determines how loud a sound is? Oh, and actually I've missed off a key portion of information, which is how fast does sound actually travel. So before I come up with what the amplitude of a sound is, let me just tell you about what the normal speed of sound is. Now, the normal speed of sound does vary depending on what medium you are talking about and what temperature that medium is at. However, at normal sort of temperatures and with air, the speed of sound is usually around 330 meters per second. However, this is not a universal constant like the speed of light is a constant. This depends on the medium that we are talking about. In this case, we're talking about air, and it depends on the temperature of the medium. Why does it depend on the temperature of the medium? Well, the temperature determines how quickly the molecules are moving. Okay, you understand now that sound is propagated forward by molecules moving. If they're at higher temperature, then they'll move forward more rapidly, and therefore the sound will move forward more rapidly. So that's why the speed of sound does depend on temperature, and of course you can understand that it's going to depend on medium as well. Okay, right, so that's the general speed of sound. So what do we mean by the amplitude? Well, the amplitude again is best understood by looking at this graph here. So we are looking, I'll remind you, at how pressure at a single point varies with time. And what we can see is it goes down and up and down and up. The amplitude of a sound is all about how big are the rarefactions and how big are the compressions. You see, if you were to hit this xylophone bar much harder, so let's now go back to having the big xylophone bar. Okay, so we're not interested in pitch anymore. We moved to having a smaller xylophone bar to discuss pitch. Now we're interested in amplitude. Let's go back to talking about the big xylophone bar. And let's say we hit that big xylophone bar really hard this time. What's going to happen? Well, it means that the actual deviation, the actual deformation of the xylophone bar is going to be much bigger. If we hit it much harder, how much it's actually going to deform down and up, conversely, will be much bigger, i.e. the size of the oscillation, the amplitude of the oscillation of the xylophone bar will be bigger. And that means that the size of the compressions and rarefactions will be bigger, and therefore the alteration in the pressure at areas will be bigger. Okay, so that is what amplitude is all about. It's about how hard you hit the xylophone bar. If you hit it very weakly, so you just tap it, then the actual size of the oscillation will be much smaller, and therefore you'll get much smaller compressions and rarefactions. Now, the really important thing to stress is that how hard you hit it isn't actually going to determine the frequency of oscillation. Instead, it's just going to determine how large the oscillation is, the amplitude. Okay, so this bar has a certain frequency of oscillation no matter how hard you hit it. It will oscillate backwards and forwards at a certain rate whether you hit it really lightly or really hard. If you hit it really hard, all that will now change is the size of the oscillation, the amplitude of the oscillation. That's a really important point to understand. Okay, so that's what the amplitude of sound is all about. How big is the deviation from the air pressure downwards, and how big is the deviation upwards? So to draw it on this picture, this would be the amplitude. So here is the normal air pressure. How high do you go up to? That difference in pressure, that change in pressure that you're actually getting there, the maximum change in pressure that you're producing as part of this sound wave, that is what is meant by the amplitude of the sound wave. Now, you can measure the amplitude of a sound wave as just the change in pressure in pascals. Okay, that's a perfectly valid way to describe the change in pressure, the amplitude of a sound wave. However, there is a way that people often use which is known as the decibel sound pressure level. And I'm just going to give you the formula for this. So the decibel sound pressure level, dBSPL. So dB here stands for decibel, and then SPL stands for sound pressure level. So this is just a formula to convert the absolute change in pressure that you get as part of the sound wave into something else, another number that represents the same thing but has slightly more complicated mathematics. But you should just understand that all this number is about is how big that change in pressure is. Okay, so I'm going to give you the formula then to convert the absolute change in pressure, the absolute amplitude, into the decibel sound pressure level of a sound. Okay, so this is the formula. You times it by 20, it's 20 times log to base 10 of the change in pressure over some reference change in pressure. Okay, and this reference change in pressure is 20 micropascals. Okay, so 20 micropascals is one of the smallest amplitude sound waves, the smallest sort of pressure change that the human ear can just about pick up, which is why we use that as our reference pressure. So what we are effectively doing is we're saying, okay, give me your sound wave, work out what the absolute change in pressure is here, delta P, the absolute amplitude, i.e. how much is the maximum compression that you're actually getting away from the air pressure here, and say how much bigger is this than the reference change in pressure. How much bigger is this than 20 micropascals? So that's what you're doing when you divide this by this reference thing. You're saying how much bigger is it? Now, the thing is, the reason that we have this log here, and this is log to base 10, so if you like I can actually just stick in to base 10 here. It's not log to base e. In a way that makes it more simple because e is a much more complicated number to understand. 10 is a far more, it's a number that you're more used to. Okay, of course e in many ways is a far more incredible number than 10, but 10 is a number that you've been aware of since primary school, so it's somehow more intuitive. Okay, right, so the reason that you're doing the log there is because the actual spectrum of amplitudes of sound that the human ear can actually detect is huge. Okay, there is a huge, great spectrum, and taking logs like this can make huge spectrums much smaller and much easier to handle. Okay, because this turns increasing by a multiplicative factor into increasing by addition of 1. So what do I mean by that? If we, for instance, went from, let's say, a number of 10 to a number of 100 here, okay, so we went from our amplitude being 10 times the reference amplitude to being 100 times the reference amplitude, you can see that that's quite a big deviation. When we take log to base 10 of this, what do we get here? Well, log to base 10 of 10 is 1, because remember, log means what power would I have to raise 10 to get 10, so that would just be 1. And log to base 10 of 100 is just 2, because you'd have to raise 10 to the power of 2 to get 100. So you can see that this changes multiplication by 10 into just addition by 1, and that's what logarithms are all about. They're about changing multiplicative increases into additive increases. So when you've got massive great variation in the sizes of the numbers that you've got here, which you do, multiplicative differences like this, you can turn them into much smaller differences, which are going to be additive differences, and that's the reason that you have logarithms appearing so often. They're to turn very big differences into very small differences. They're to change multiplicative increases into additive increases. So I hope that kind of gives you a little bit of intuition as to why someone long ago wanted to make this definition to work with. And by the way, there is nothing special about this. This is just a human definition. It's man-made. Someone long ago decided that this was the way we were going to handle the amplitude of sound. Okay, and we've been stuck with it since, but they could have decided something very different. There's nothing special about this. This is man-made, and this is far more intuitive to understand, but this is something that you will see a lot of the time. It's something that you just have to understand and use. Okay, so you take log to base 10 and then you just multiply it by 20 to get the decibel sound pressure level of a sound. Okay, so that is what is meant by the decibel sound pressure level, and although this is a complicated formula, I hope you understand that the only variable in here is this. So the answer that you get completely and utterly depends on what number you stick in here. This is a constant, this is a constant, this is a constant. The only variable here is delta P, so the answer you get in is just an altered version of that absolute amplitude, a complicatedly altered version, but just an altered version. So the number that you get here just represents how big is that change in pressure that you've actually got there, okay? And the bigger this number is, the bigger the alteration in the pressure that you're actually getting as part of that sound wave. Okay, right, so there is my discussion of what is sound. What we're going to move on to now is we're going to start looking at the auditory system. And by the way, if you've got through that portion, that's the most complicated portion of this entire video, understanding the physics of what is sound. Everything from now on is just biology, and it's just anatomy, and it's very nice. Okay, so we're going to start off with a bit of anatomy. And we're going to start off by looking at the anatomy of the external portion of the ear, the portion of the ear that you can actually see. Okay, the thing that most people would just refer to as the ear, however we'll see that the ear actually consists of much more than just this. Okay, so the portion that we can see, the external ear that is on the side of our head, and of course we've got two of them, the fancy word for it is to call it either the auricle or the pinna. So these are two more fancy names for the portion that most people would just call the ear. Okay, so what I'm going to now draw then, I prefer the name auricle to pinna for some reason, so I'll call it the auricle. So what I'm now going to draw is a picture then of an auricle. Now, the best way to do this anatomy is to feel it on yourself as you're doing, and luckily you can very easily feel your ears and feel the different portions of it. So I advise you to have your hand on your ear as we go through this, because my picture is likely to be quite bad, and if you feel the portions on you as you go through it, you'll understand it far better. Okay, right, so we'll go for the left ear then. Okay, so that I can feel the ear with my left hand as I'm drawing the picture. Okay, so here we go. So here it is at the front, and then we'll come round like so. So that's not actually a too bad shape. So we'll start off with the bits that everyone knows. So here is the ear lobe, okay? And then of course round the outside, and I'll just have this going a bit further actually, round the outside you have a fold of the cartilage, which is known as the helix. Okay, like so. So this is called the helix, and be feeling this portion on yourself as you are drawing this picture. So the helix is the bit around the edge, the fold or outwards rather, the fold over of the cartilage. Okay, that's the helix, the boundary of the ear. Now, as the helix comes down, follow it with your fingers. You can see that it sort of ends and then just goes into the ear lobule. But if you feel carefully, you can feel that it sort of continues on as this little sort of uprising from the lobe here. Okay, and this is known as the antitragus. So there is a little sort of bit that comes up, a little spiky portion of the cartilage up from where the ear lobule is, or ear lobe is. So this is what's known as the antitragus. Now, we've had the antitragus, but where's the actual tragus? So now what I want you to do is feel with your finger and find the actual entrance to the ear canal. And you'll see that there is this little portion of cartilage that covers that up, another little spike of cartilage, and it's in this sort of position here. Okay, like so. And this is what's known as the tragus here. So I'll just label that up as the tragus. So this is the tragus here. Okay, so you've then got this little notch in between the antitragus and the tragus, which hopefully you can put your finger into now. Okay, and that's what's known as the intertragal notch. So this little notch here, little space, is called the intertragal notch. Okay, so now let's sort of continue it on. So we'll draw this up here. So the entrance to the auditory canal, the external auditory meatus, and I'll write that down because that's a very key term. So the name for the opening into the auditory canal is known as the external auditory or acoustic. So you can call it the external auditory, or you can call it the external acoustic meatus. Meatus is just an opening, and that is, I can't really put it on this picture because that's underneath the tragus, and if you feel it on yourself, you'll agree with that you can't actually see it from the left-hand side. You'd have to sort of go under the tragus and in at that sort of angle to actually find the external auditory or acoustic meatus. But it's there. So we've had the helix, the intertragal notch, the antitragus, the lobe, the tragus. The next thing I think to mention is what's known as the antihelix. So again, go back to your ear and feel the cartilage portion here, and you'll see that the cartilage sort of has a ending, well, not an ending, has a ridge where it suddenly goes down, and this is what's known as the antihelix. So there's a portion here, like so, known as the antihelix, and this comes down like this, and the antihelix is this dent, effectively, in the cartilage, this corner of the cartilage. And if you feel up in the superior portion of the auricle, you'll feel that there are two sort of ridges of cartilage that are both part of the antihelix, one that goes up here and one that goes down here. Okay, and those are known as the crura of the antihelix. Okay, so these two ridges here are known as the crura of the antihelix, and this little space in between the two crura of the antihelixes, and again, feel this on yourself. So follow this portion round, try and feel this portion. This one's much less obvious than this one. This one's very easy to feel. Try and feel this one as well, and you'll feel that there is this sort of space demarcated by those two boundaries and the helix in front, and this is what's known as the triangular fossa. So that space there in the auricle is called the triangular fossa, and I'll just colour in the triangular fossa here in red. Okay, so we've had the crura of the antihelix. I haven't actually labelled on the antihelix. The antihelix comes all the way down and then sort of finishes down here where the antitragus is. So this is the antihelix here. So we've almost completed up the different portions of the auricle that actually have names. The final thing is to give these cavities here. Oh, actually, just before I give these cavities names, let me tell you what the name for the end of the helix is here. So when the helix, if you follow the helix round, okay, right down into the sort of space in the middle here, this portion as it sort of tapers off at the back, this is known as the crus of the helix. So this is another thing to put a name on. So this is the crus of the helix. Right, and the final two things that I want to label up on here are the names for these spaces in the centre here. The name for this space here and the name for the space here. Okay, so the name for this space here, which is below the antihelix but above the crus of the helix, and again, feel this on yourself, that space, hopefully you've got your finger in it now, that's known as the cymba conchae. Okay, so the cymba conchae is the name for that space there. Finally, this space here, which is below the crus of the helix and in front of the helix, in front of the antihelix here, and if you follow it forward, you can go underneath the tragus into the external auditory meatus. That space here, which I'll colour in yellow here, all of that space, that's known as the cavum conchae. Okay, so those are all the different portions of the auricle that have names. As I say, the best way to do this is just to feel them on yourself and give them names, because it's difficult to draw the auricle or the pinna as a picture, and the best way to do it is just to use the ones that you have and name the bits on yourself by feeling them. Okay, so that's the anatomy of the auricle or the pinna if you prefer that name. What we'll do now is we'll have a break, and in the next video we will talk about the anatomy of the temporal bone, and then we'll follow, we'll go inwards and we'll have a look at the more inner portions of the ears. We'll have a look at where the external acoustic canal actually takes us. We'll have a look at the middle ear, and we'll start to have a look at the labyrinth.